Okay, hi again everyone. It's Professor Sebastian. Welcome back to our the last page, page 35, last example in our section 13.4 notes, example 33. So before we get to that, let's look at the definition of principal unit normal vector. At a point where the curvature is not equal to 0, so if the curvature equals 0, this does not work, but at a point where the curvature does not equal 0, the principal unit normal vector for a smooth curve in the plane is defined as such. So the normal vector is 1 over the curvature times the rate of change with respect to arc length, dt ds, of the unit tangent vector. So we can manipulate this a little bit, right? So we know that curvature is defined as 1 over the speed, 1 over the magnitude of velocity times the magnitude of the rate of change of the unit tangent vector, dt dt. So we can flip that over, so 1 over curvature would be the speed, magnitude of velocity divided by the magnitude of the rate of change of the unit tangent vector, dt dt, times dt ds. And then we can just kind of manipulate this a little bit algebraically. So we have the TDS right here, and I can multiply that times ds dt, because that's another notation for speed, or the magnitude of velocity, divided by the magnitude of the rate of change of the unit tangent vector. So when I simplify that, this becomes dt dt, the ds's cancel. I get dt dt, rate of change of the unit tangent vector with respect to its parameter t, divided by the magnitude of that. So this also then is a unit vector, and we know that it is normal to the curve. So it's defined as t prime of t, or the rate of change of the unit tangent, divided by the magnitude of t prime of t. So for example 33, let's find that principal unit normal vector for the helix in the previous example, and then describe how that vector is pointing. So first of all, we need to find t prime of t. So if you look back up here, here is t. This is t right here. So if I take the derivative, the only thing that has the parameter in it, t, is sine of t. So the derivative of sine t is cosine t. Derivative of cosine t is minus sine t. These are constants. They'll stay with it. And then this is a constant all the way around, so the derivative of that will be 0. So the derivative of the unit tangent is minus a cosine of t divided by the square root of a squared plus b squared in the I direction, minus a sine of t divided by the square root of a squared plus b squared in the j direction. So if I take the magnitude of that, square minus a, I get a squared. Square cosine, I get cosine squared. Again, I get a squared here and sine squared, so I can factor out the a squared. A squared times cosine squared plus sine squared, which we know is the Pythagorean identity, that's equal to 1. So I get the square root of a squared over a squared plus b squared. Because when I square these guys, they just become a squared plus b squared. And then I'm taking the square root of this whole thing. So that becomes a, because a itself was described as a positive constant, so the square root of a squared is a. Don't have to worry about absolute value because we know a is positive, divided by the square root of a squared plus b squared. So the unit normal then is t prime divided by its magnitude. So if I'm dividing by its magnitude, which is a fraction, I'll just invert that fraction and multiply. You can see that the square root of a squared plus b squareds in each term cancel, and the a in each term cancels. So I get minus cosine of t in the I direction, minus sine of t in the j direction. That's easily verified to be a unit normal, a unit vector. Right? The magnitude of this would be cosine squared plus sine squared under the square root, which is square root of 1, which is 1. So what does this look like then? Well, it means that, now imagine we had this helix. So if you go back up to the top of the page, we had this helix, which is a circle with a radius of a, parallel to the xy plane, and then climbing the z-axis. So I kind of have had you thinking about a hang glider that was climbing up. You know, there's some kind of updraft bringing it up, circling around the z-axis. So this unit normal vector, you can see, always is parallel to the xy plane. There's no z component, and it always points toward, right directly at the z-axis. So the unit tangent vector is always going to be perpendicular to that. And as a matter of fact, it always will for every curve. The unit tangent and the normal principal unit normal are going to be perpendicular, so their dot product will always be 0.